In this lecture, let us discuss the design of sequential circuit using JK flip-flop. And we know that we are discussing and we were discussing the manual synthesis procedure or manual design procedure. Okay, we are not using logic synthesis tools. Therefore, the manual synthesis procedure for sequential circuits with the JK flip-flops is the same as with the D flip-flops. But the only problem is you cannot get the input equations for the sequential for the flip-flops directly from the state table, right? So, for input equations, the input equations must be evaluated from the present state to the next state transition. So let us consider this state table. Okay, so if it is a D flip-flop, directly you can write from this. Directly from this you can write down the input equation if it is a D flip-flop. But here we are going to discuss with the F flip-flop, JK flip-flop. So to illustrate the procedure, consider this second state table, and then we will derive the flip-flop input equation. Okay, so we have present state, next state, and input. In addition to these three attributes, we have one more attribute called flip-flop inputs. Okay, so we have present state, input, next state. This is conventional state table has. Okay, if you take any conventional state table, it has present state and what is the input and what is the corresponding next state, and of course output. Okay, but here, in order to derive the input equations for JK flip-flop, we need something extra that is called flip-flop inputs, and that is derived from the excitation table. Okay, so therefore the flip-flop inputs are derived from the state table in conjunction with the excitation table for the JK flip-flop. This is very easy to fill it up these four columns. Once you know the JK flip-flops excitation table, then it's very easy to fill it up, no issues. Okay, now look at the table very clearly. Look at the table very keenly. Then now let's see how these combinations are coming. Okay, and 0x, 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 1x, all those things. Okay, so if you take present state and next state, let me take the first row 0 0 and here also 0 0. Okay, so we have a transition for let me consider first a flip-flop A alone. We have a transition from 0 to 0, right? So for flip-flop A, so 0 in the present state, 0 in the present state to 0 in the next state, right? So now one should ask a question, which input will lead to this type of state transition, right? For the JK flip-flop, we find that in the last lecture, the transition of states from present state 0 to next state 0 requires that J input must be 0 and K input must be a don't care condition. So therefore 0x. So whenever you find 0 to 0, then there you fill it up with the 0x. Similarly, look at here also 0 to 0, so you put 0x. Here also 0 to 0, you put 0x. Okay, and what did I do? I'm sorry. I'm really sorry. Okay, so I confused. I'll come back. Okay, now this is fine. Okay, 0 to 0, no problem, 0x, and then this 0 to this 0, you have 0x, and this 0 to this 0, again 0x, and this 0 to this 1. Now you have the transition from 0 to 1. Okay, so 0 to n, what shall we do? We are moving from 0 state to 1 state, that is we are setting the flip-flop, right? So therefore the second row shows a transition for flip-flop B from 0 in the present state to 1 in the next state. Okay, from the excitation table we find that a transition from 0 to 1 requires J must be 1 and K can be a don't care condition. So that is why we put here, where is it? Yeah, 1x here. So 1x is 0 to 1. So likewise you can complete this entire thing here. Okay, so this process is continued for each row in the table, and for each flip-flop with the input conditions from the excitation table copied into the proper row. Now the flip-flop inputs are known, and these inputs are as a function of the present state and the next state, I'm sorry, not the function of next state, it is a function of purely the present state and the input. The moment you give 0, when the machine is in state 0 0, see, the machine is in state 0 0, the moment you give 0, it goes to 0 0. When the machine is 0 1, and the moment you give 0, then it goes to 1 0. Therefore the next state is a function of the present state and the input. Also the flip-flop input also as a function of the present state and input. Therefore I can find out what is JA. From this I can find out what is JA. From this I can find out what is JB and all those things. Now in order to find out JA, look at the JA column. So in the JA column, let me clear, make some space. JA column, then I have M21, this one M21, and then all don't care conditions here. Therefore JA is, you combine these two guys, JA is BX bar. Similarly for KA, what you do, take another K map, and then this all are don't care conditions, and this is only one. So combine this, and this is KA is BX. Okay, and then for JB, this is 1, X, X, X and X. You take this quad, so JB is X. By the way, this is A and this is BX. A, BX, this I did not fill here, so you can fill it up. BX 0 1 0 0 0 1 1 1 1 0 0 0 0 1 1 1 1 0 0 1. So this is straightforward. Okay, JB is X, and then similarly you can find out KB. KB is little complex. Okay, so let me draw the map, and here this is X, and this is 1 X, X and 1. Just to fill the see, this is 0 1 2 3 4 5 6 7. Okay, so these are the min terms. So how will you combine here? This one and this don't care you can combine, and then these X and 1 you can combine. So if you write down the Boolean expression for this, then AX plus A bar X bar, and don't you know this is A exclusive OR of X and whole. So this is the XNOR operation. Okay, XNOR operation. So I got 4 expressions now: JA, KA, JB, KB. And note the next state values are not used. Okay, the next state is the result of this input equations. Okay, so please consider and don't get confused, and see, the next state values you are not supposed to use while deriving the flip-flop input equations. Why? Because the next state is the result of your input, okay, which you are applying the applying your flip-flops. Okay, so the next state values are not used during the simplification. Okay, during the simplification of your K map. Okay, since the input equations are a function of the present state and the input only. See, our aim is we need to derive the input equations. So in the input equation is the function of present state and input, not the next state. Next state is the result of your input equation, your result of your flip-flop inputs. Now note the advantage of using JK flip-flops. See, in the D flip-flop I said directly you can write down the input equations, but in the JK flip-flop you have some advantages. Okay, when sequential circuits are designed manually. Okay, what are the advantages? Number one, the fact that if you go through the state table flip-flop inputs, there are so many don't care entries. So this don't care entries will help us to get a simple Boolean expression. Okay, for example, in this case, if I don't have this don't care condition, then I'll get this expression. Okay, so I'll get this one. So this one is it has one more, this is 0, 0, 0, 1. That means this is b bar x. So if you have don't care, then it would have been b bar x. But because of this don't care, I got a simple expression x, jb equal to x. Therefore, whenever you have don't care conditions, you'll get a simple Boolean expression. Okay, so in this table, if you look at, there are so many don't care entries. So this don't care entries indicates that the combinational circuit for the input equations is likely to simpler. Okay, look at here, it is a simple input, jb is x and j is bx bar and k is bx. Of course, certain conditions you can't avoid. Okay, so you have to live with that. Okay, therefore, because don't care min terms usually help in obtaining simpler expressions like this, and so simpler expressions we will get it. And the second advantage is, if there are unused states in the state state table, there will be additional don't care conditions in the map. For example, you start from 0, 1, 2, 3, 4 and 5. You stop there. 7 and 8 are don't care conditions. So again, that will give a lot of simplification while simplifying the K map. Okay, so because these unused states all are denoted by, generally in digital circuits, unused states are denoted by don't care condition. Don't care condition. Okay, and even though you have this unused state, helps to get simpler Boolean expressions or simpler expression. So these are the two advantages. Now, nonetheless, D-type flip-flops are more amenable. More amenable to an automated design flow. So whenever you want to do some automated synthesis using some tool, then D flip-flop is more amenable. So this is mostly used in industries. Used in industry. Now let us construct the circuit. So you have two flip-flops. Okay, and this is A flip-flop and this is B flip-flop. This is JA, input KA, JB, KB. This is A and this is A bar, B, B bar, JA, KA, JB, KB, and then this is clock. Okay, so now what is JA? JA is BX bar. You take X here and you put a NOT gate and then put an AND gate. Okay, bx bar. So you take b from here, bx bar. Okay, ja is over. What is ka? Ka is bx. So put another AND gate. This is b, and this is x. So bx. What is jb? Jb is simply x. Finished. What is kb? Kb is XNOR operation. So I put an XNOR gate, and the inputs are what is the inputs? A and x bar. Okay, so I have to bring my a. Where is a? It is somewhere. Yeah, let me just take this a, bring it a, and x. I can take from here. That's it. And this is clock. Okay, so this is the logic diagram or schematic of the sequential circuit using JK flip-flop. So simply I have taken one arbitrary state table and we derived the flip-flop inputs. Okay. So the only thing is you should know the excitation table, that's all. So when your flip-flop moves from present state 0 to 0, what is the input for the flip-flop? 0 to 1, what is the input? 1 to 0, what is the input? 1 to 1, what is the input? These four things we should know. 0 to 0 means 0x. Like that you should remember. Okay, so that's it. So let me stop here. In the next lecture we will discuss how we design the sequential circuit using T flip-flop. Okay, T means toggle. So that we will discuss in the next lecture. So let me stop here. Thank you very much.